Hi, my name is David Boyd, and I'm a scientist at the California Institute of Technology. It's in Pasadena, California, just outside of Los Angeles. And I work in the Department of Physics, or condensed matter physics. You might be familiar with the TV show, The Big Bang Theory, which takes place at Caltech. For us, it's a bit more of a reality show than a comedy. But I will say, in the true version, there's more than one Sheldon. There are many Sheldons. So I'm really excited to be here, and I'd like to tell you the story about this discovery that we had on graphene. And I want to view this really from the lens of looking at this from serendipity and a bit of history and putting sort of data and making connections, rather than going through sort of the physics of this, which I'm sure would interest a lot of people. But I think the story of serendipity really fits in the spirit of the World Technology Network. So I'm going to begin with a little bit of a background. Our discovery was on graphene. We had a new way to make graphene. And I'm going to tell you a little bit about what graphene is, in case you don't know, and kind of describe the setting for this. And I'm going to talk about the discovery that we had that led to this, and kind of the journey that we went through on this discovery. With no further ado, OK, graphene the Great. Graphene is simply a single layer of carbon atoms, and it has magnificent properties. People had been aware of graphene, or theorists had been aware of graphene for many years. Graphite is simply layers of graphene. Coal, for example, is a form of carbon, graphitic carbon. And the idea why graphene has gotten a lot of attention is that when graphite was being discovered back in the 40s, they needed a theoretical construct to study graphite, and they used graphene, these thin layers. And they said, oh, these amazing properties that it has. The problem is we can't isolate a single layer of this material. It would be impossible. So for years, there were all these theoretical applications, all these properties that it had, but no one was able to actually isolate single layers of graphene. Along until around 2006 through 2010, when Andrew Geim and Nosolovic were awarded the Nobel Prize for actually isolating graphene. Now, what's important about this is that some of these amazing properties is that it's stronger than steel, yet flexible. It's more conductive than copper, yet transparent. So you now have a transparent, flexible conductor. So the applications of this are really quite limitless, and I'll go into that in a few minutes. But as you can see here, graphene will start with graphite, just layers of graphene. It looks like a piece of chicken wire, where these are carbon atoms all stuck together. It can form a flat sheet. This is graphene. It can be rolled up into a nanotube or into a fullerene or a buckyball. So the discovery for graphene, or the 2010 Nobel Prize, was what I like to call graphene fabrication 1.0. You start with a pencil, which is this is your standard pencil. It's a graphitic tip. This is graphite. You have Scotch tape. You stick this off on your pencil, pull this off, and voila, you get microscopic bits of graphene. And folks, this is literally what won the Nobel Prize. And no joke, the Nobel Prize Museum, they gave them a roll of Scotch tape in the commemoration for this. So again, these are pencil, Scotch tape, and little tiny flakes of graphene, about the size. This is about 100 microns, so very, very tiny. So the applications for graphene are almost limitless. One of the great properties of being a transparent, flexible conductor is that it could go onto solar panels as a current collector. It could go on your touch screen, your device. And it has incredibly high electrical conductivity, so it can go into all sorts of advanced electronic devices. So again, solar electronics and sort of advanced computational electronics. The only problem is that if we go back, you can't really do it with these tiny bits of graphene. And this is, although it has amazing properties, the best properties they've found so far are from these tiny bits of graphene. It's not a scalable solution. It's a technologically relevant solution. So there's a real need for large area synthesis of graphene. So this is what I'd like to call graphene fabrication 2.0, chemical vapor deposition, We're in the business, we just call it CVD. It's a very simple process. You heat up a substrate, in this case copper foil, you put it into a furnace, you heat it up to about 1,000 degrees C, you add in some hydrogen and methane, and voila, you get graphene. And so the fellow that discovered this is out of Austin, University of Texas, Austin, Rod Ruoff. Great discovery, had worked in carbon and diamond for years. Typically done in the lab, what you have is what we call a tube furnace. It's simply just like it sounds. You've got a furnace with a hole going through it. You can flow in gases, and you're able to control the pressure. But again, it's a pretty simple process. When Rod did this in a science paper in 2009, I was amazed, because I do work in the field of CVD. And so to read about something, and we make very complex films. We have big elaborate reactors to make these complicated materials. And to see all this attention going to something that's so simply of copper, a furnace, and methane I was like, wow, I should be able to do this. So I got interested on this and doing this in my lunch hour. I figured, hey, I've got this equipment. It's easy enough to do. It's just something, it was an unfunded experiment. I started playing with it on my lunch hour. I said, I should be able to repeat this process. Well, unfortunately, I could not repeat the process. I followed the recipe very carefully. I heated the copper foil up, 1,000 degrees C, and I couldn't get this to work. It didn't work the first time. It didn't work the second time. Again, I'd heat this up, underflowing hydrogen, I'd add methane, it didn't work. It didn't work, it didn't work. So then about the nth time, as I was trying to do this, I couldn't figure out what was going on. Now in our laboratory, we have a special instrument that can tell us whether we have graphene or not. So I'm able to grow this, I can tell if we have graphene, we don't have graphene. It wasn't working. So one of the times, the nth time I was trying this, I got a phone call right as the thing was heating up. I think someone was calling, my buddy Tom was calling to tell me about the surf report in Malibu or something. And I got distracted, and I didn't turn the methane on. So it sat at high temperatures and cooked for a while in pure hydrogen. Well, lo and behold, this time it did work. So we ended up going beautiful, beautiful graphene. Now, the reason this worked this time was because at this point, people didn't quite understand the graphene growth process. I don't think Rod even really understood it that well. But you need to have an absolutely clean copper surface on which to grow. And so what I saw after the run is I saw all these bits of copper. So inside here was the piece of copper. This is my furnace. It got very hot. These are the cooler ends. Now, copper has a native oxide on it. And what happens at high temperatures in hydrogen, this copper comes off and cools off. The copper oxide is reduced. And so instead of being red copper, which you normally see like on a penny, that's because of copper oxide. Once you remove that oxide, it becomes very bright and shiny. So what I realized after seeing this was that the only reason this grew, this is the first time we saw this, is that we had all the copper oxide was removed. So I said to myself, well, that's it. If you can clean the copper off and then just add in the methane, you should be able to grow graphene pretty easily. And the reason, and so that's a good thing. So a downside with, let's go back, with this kind of CVD graphene fabrication is that you have to go to very high temperatures. It's 1,000 degrees C. It's not compatible with the existing electronic manufacturing. So at 1,000 degrees C, your electronics are going to melt. So if you want to put this technology into a fab and into a semiconductor fab or any kind of electronics, you've got to drop down the temperature. 1,000 degrees C is too high. So my thought was, if we could cool the process down by maybe cleaning the copper another way, we'd be in good shape. So I thought back, and copper oxide has been kind of a real bugaboo for a lot of things. It's very reactive, and so it's not like you can clean it and then start growing on it because it oxidizes almost immediately. And the issue with hydrogen annealing at high temperatures is really to remove this native oxide. So the idea was if I could find another way to do this at lower temperatures. So Robert Millikan, who was one of the founders of Caltech, had done an experiment a few years back where he had to deal with copper oxide. He was trying to remove the oxide and wanted to do it in a way that did not get any oxygen on it. So I recall back from way back in my college days, a professor, Tom Dowiak, that told me about this famous experiment. This is Tom Dowiak. He's a professor at the University of Alabama. And this is Tom. He was involved with the Mars rover mission at JPL. He was a great experimentalist. And he mentioned this experiment that Millikan had done where he had actually gone and built a basically a machine, a cutting tool, a lathe, inside of a vacuum. And what this allowed him to do was to actually clean copper. He was able to measure Planck's constant back in 1916. So I thought, hey, if I could find some way to actually clean the copper in situ under vacuum, I could do it. I wasn't going to build a machine system like this. This is rather complicated. But we do have a plasma system in our laboratory. We happen to have this because of Dave Goodwin, worked in Diamond. And we had a plasma. So the idea was if you could create a plasma, which is simply just like your microwave oven with a gas in there, you would be able to clean the copper and have a clean copper surface. Well, lo and behold, I tried this. We happen to have this plasma system. I hooked it up to clean the copper, and lo and behold, cleaning the copper worked the first time. My intent was just to clean it and then try to grow on it, but in fact, it grew the first time. And in fact, the graphene was very, very good. In fact, it's the best graphene that, quality-wise, that has been synthesized to date. Okay, so to make a long story short, why did this happen? What would happen in this plasma is a very reactive environment. To begin with, we had leaky valves. We had a small amount of methane was leaking into the system, just the right amount. We also had amount of nitrogen, a very small atmospheric nitrogen was also leaking into the plasma. Methane and nitrogen combine to form a chemistry that allows you to clean the copper at room temperature. It also allows you to smooth the copper at room temperature. Copper is very difficult to clean, but now we found out a way to do this at room temperature. The chemistry was also just right. What allowed happen was also the copper to be clean, the copper to be smooth, and then graphene to grow at the same time. So all in one step, this worked. The process resulted in nearly perfect graphene. It happened at much lower temperatures, at CMOS-compatible temperatures. We had very high electron mobilities, higher than that had been recorded. The process is very fast. And furthermore, we could grow multiple layers. Unlike the thermal methods of CVD, which only grows a single layer, we can grow multiple layers of graphene. So, summary, in terms of serendipity, we were prepared. I mean, chance favors the prepared mind. But we did have the case of a phone call, some leaky valves, a leaky vacuum system. And again, these valves were leaking in just the right amount. We found out later that any more or any less, the process doesn't work. And we happen to have this system away. But most importantly, I was standing on the shoulder here of giants. Professor David Goodwin, who was a pioneer in diamond work, Professor Tom Dowiak, who had a great knowledge of experimental work, and Robert Millikan's experiment from 100 years ago. So I thank you for your time, and hope you enjoyed the story.